Hi, welcome to SPE Live. It's great to have you back. My name is Nils Kaageson-Loe. I am your host for today. And if you are new to SPE Live, well, check us out on social media, #SPE Live, or find us on SPE.org. SPE Live is made possible by sponsorship from the SPE Foundation. So today we begin a journey looking at wellbore quality, wellbore integrity, production impairment, and economic value lost. And today's specific question is, how true is your track? So wellbore surveying is what we're looking at and talking about today. So do you know your true well path? Did you miss the reservoir sweet spot because of your location is in error? Is your well path so dog-legged you risk casing deformation when you're running casing, or failure to complete your well as planned, or even re-entering the well is a big problem? Did you drill too fast? So today is wellbore surveying. So we'll meet the guys in a minute and talk about that in detail. In a week's time, we continue this conversation with George King and Neil Nagel about their observations on casing deformation in unconventional wells. So it really builds on today's conversation in many, many ways. So George and Neil, they'll be looking at causes and consequences of casing deformation in unconventionals. But today we have to begin our journey by actually looking at how do we survey wellbores. What do we know about their condition in terms of integrity and doglegs and that sort of thing? So taking greater care of our wellbore assets equates to greater asset value. So that's the nugget of this journey, right? If it's your first time joining us on SPE Live, interact through the chat boxes on social media. Tell us what you think, share your comments, tell us where you're viewing us from, ask questions of our experts today. And if you know people who are interested in wellbore surveying and wellbore integrity, then repost us, tag us on social media to all the people that may be interested. So let's meet today's guests. Joining us today are Adrián Ledroz and Rob Shoup at Gyrodata. I'll be asking them questions and talking about what is the value of wellbore surveying and what are the technologies, how does it work, what are the barriers to adoption. So let's meet Adrián and Rob. So Adrián is Vice President of Technology at Gyrodata. He serves as a primary technical expert on downhole surveying and inertial sensors. He oversees the company's survey systems development group for all downhole directional tools. He also serves as the program chair for the industry steering committee on wellbore survey accuracy. Previously, he worked as a research and development engineer, technical services manager for gyro surveying, and project manager for new technologies. He holds a BSc in biomedical engineering from the University de Entre Rios in Argentina, and an MSc in electrical engineering from the University of Calgary. Also joining him is his colleague Rob Shoup. Rob is the Operations Technical Support Manager for Gyrodata. In this role, he works with engineering, product line, and operations to develop new technologies and solutions designed to overcome the challenges of the modern oil field. Over 32 years, Shoup has held a number of senior leadership positions at Gyrodata, including VP Special Projects, North America Regional Manager, Global Technical Service Manager, and Senior Technical Advisor. He spent 5 years in the field running gyroscopic surveys and orientations and integrating Gyrodata's technology with various service providers. He's also an active member of SPE and on the industry steering committee on the Wellbore Survey Accuracy Group. He graduated from the Institute of Electronic Science at Texas A&M University. So, gentlemen, welcome to the show. It's good to see you all.
Thanks, Neil. Good morning.
Thank you very much.
Good morning. So, like I said, we're going to be talking with you guys about wellbore surveying technologies and the state of the art. Wellbore surveying is a critical element integrating many functional disciplines from drilling, completions to production. So hopefully we can delve deeper into that in today's conversation. So maybe let's start off with some high-level understandings of what wellbore surveying is and what it does. So, Adrian, tell us a little bit from sort of high-level point of view. What does wellbore surveying help us in terms of understanding uncertainty in the well path and that sort of thing? What's the value add?
Yeah, we should probably start with why we survey wells on the first place, and that also takes us back to why we drill the well in the first place. So we drill the well to produce hydrocarbons and to do it on a safely way. So in order to know that we are actually achieving these goals, we need to survey the well. So what we do is we need to measure the trajectory to hit the reservoir, which is the way that we're going to get the hydrocarbons, obviously, but also to avoid hitting other wells. And we need to produce documentation for the regulatory agencies, as well as we can use this information for, as you mentioned, running casing, establishing the quality of the well, and put down production equipment and do all that in a safe way.
Okay, so what kind of value add is it? In terms of running wellbore surveys, what sort of advantages does it have in terms of saving drilling time or accuracy in wellbore placement? Can you just give us some headline figures around that?
Well, of course, if you don't survey the well, then you don't know where you are drilling. I mean, the time that we drill just a vertical well, and here the reservoirs are long gone. So the value is that, well, if you drill a dry well, that's going to cost you a lot of money. If you drill a well in which you collide with another producing well, you may have a blowout with very severe consequences. And if you can keep going down that line, I mean, if you drill a well and then you cannot run casing, then that also becomes a problem, and you cannot use that well. So to do a proper job on the survey, obviously, like everything else, you need to follow the procedures and have a standard quality control measurements, and all these take a bit of a background effort and take takes some additional time that you cannot just drill blindly. But of course, there is a good balance, and when you start shortcutting the survey, then you pay a very high price, especially if you face with a collision or something of that magnitude.
Okay, thanks, Adrian. So potential time saved could be like 1 or 2, even more days in the overall operations. Rob, talk to us a little bit again from a high-level perspective as we sort of step into this. What are the different types of technologies we're looking at? We've got conventional wireline runs, and also you guys have gyro while drilling. Can you tell us a little bit more about those two aspects of this technology?
Sure. So to begin with, let's just talk a little bit about the history where this all came from. Most wells are drilled with magnetic instruments. They have been for years. The earliest magnetic instruments was nothing more than a bar magnet on a compass card with a plumb bob over the top of it. That was developed in the early 20s. John Eastman was instrumental in doing so. Came from the acid bottle survey. And magnetics came in. That's when magnetics actually came into play. Gyros came into play shortly thereafter by Sun Oil Company, a gentleman that was actually knew that they had problems with these magnetic instruments. So he contacted the SPE gyroscope company, and the first gyros for oil wells were actually developed. And a little company called SPE Sun was actually formed from that. They still manufacture and still run these conventional gyros today. They operate off the principle of inertia. So they don't know which direction they're pointed. You have to actually sight these in to a known direction, and then it will attempt to hold its plane of reference throughout the survey. From that, over the years, they knew that there was an issue. There was a study done by a couple of gentlemen, Wolf and DeWart, showing the inaccuracies of surveys. And that kind of opened everybody's eyes. And that kind of was when Gyrodata was founded. off of a gyro system that was built for the aerospace industry. And that was, we mentioned this earlier off the air, but that was 40 years ago this month that Gyrodata was actually founded using this technology. And since then, we've developed several different systems with different gyros. We got to the point where we had to actually develop our own gyro because there wasn't anything on the market. But so we've come a long way in surveying in the early, or I should say late 80s, more so. The fluxgate magnetometers, solid state systems came into play, and they kind of took over. Early on, it was steering with magnetic steering tools on wireline, where you had to actually enter the drill pipe, and then the wire would run down the outside of the drill pipe, which caused a lot of problems. And ultimately, the pulsar was invented so that you could do away with wireline.
Okay,
so that being said, we still actually gyro steer on wireline, and it's typically a function of finance, right? It's cost, what people are willing to pay. But what we found is that since the inception, we started gyro while drilling technology in 2002. And since then, it's evolved quite a way that we can talk a little bit about more. But by running a gyro while drilling, it gives you the advantage of not having the HSE issues with wireline, which is a big problem. And obviously, everybody wants to operate in a safe manner.
Okay, great. So let's talk a little bit more about then these different types of gyro systems. So you mentioned there the gyro while drilling and also the solid state instruments. So what other instruments do you guys, or what are sort of kind of standard instruments in the industry now, and what are some of the new developments that you guys have? Adrián, perhaps you want to sort of talk about that?
Yeah, we've been using until recently the spinning mass gyroscopes that are very accurate, but they can suffer from changes in the calibration or get damaged due to the drilling environment. So in 2018, we launched our first product using a solid state technology. So basically, this is instead of having a traditional spinning mass gyro, this is closer to an electronic chip. That we work with a company that's been building solid state gyroscopes for many years and modified the sensors to be able to withstand the downhole environment and also to give us the accuracy that we need. So we started using that technology, and it gave us a lot of advantages and have been seen by many people as a really a breakthrough on the fact that we can survey now much faster than before compared to the other gyroscopes, and it takes less power and is a much more reliable sensor. So we now have something that is similar to as Rob mentioned, the solid state flux magnetometer that we can take the shock and vibration. So we are making a lot of progress on that area. So the first tool was a drop tool that you run when you reach certain section of the well, and then just pull out of the hole and make a survey as you pull out of the hole. And we are running now. We've been doing the first commercial runs with the solid state GWD tool, which obviously you get the survey in real time, so you can steer the well, and we have used that in many wells from the top to the bottom, which is something new for a gyro, and with the added advantage that in most of these runs we have magnetic data as well from the NWD. So now we have these two instruments that you can compare one against the other, and you can eliminate gross errors, and you can validate that there is no parameter outside specification. And even if you want to go farther, you can combine the two surveys and even reduce the uncertainty, which is really an advantage when you're looking at the extended reach wells or wells yeah, they're very long.
Adrián, let's pick up a little bit on that. So what is the significant difference between MWD data and GWD data, for example? How much value is there, additional value is there in having GWD in the well relative to MWD? Can you say a little bit more about that?
Yeah. When we started, the GWD was mostly for helping in areas of magnetic interference. So basically, you needed to kick off a well, and you have another well or another casing or set of casings nearby, and therefore the magnetic data was really corrupted by this. So a magnetometer measures the Earth magnetic field and basically a compass, but so you use that information to drill the well, to steer the well. But when you have magnetic interference, that measurement is no longer reliable. So you need another way of dealing with that. And that was the initial GWD that we launched. It was down only to 20 degrees. It was it was not very accurate, but that was a way to get by there. But what we have achieved over the year is to increase the accuracy of the tool. So now the latest run has not only been to help with areas of magnetic interference, but also to reduce the uncertainty at the end of the well. So when you are facing fields with a lot of wells that are congested, you're gonna face magnetic interference every now and then, but you also need to reduce your uncertainty so you can drill near the other wells reducing the risk of a collision.
Okay.
So gyroscopes, they measure the Earth rotation instead of the magnetic field. So that has the advantage that is not affected by magnetic interference from the drill string or magnetized mat or any deposit that may be downhole.
Oh, okay, thanks. So that's good to have that clarification on the differences there. Rob, can you sort of give us some examples of, Adrián was talking there about the accuracy of the well path, and particularly in situations where there's a lot of wells close together in close proximity. Can you give us some more sort of clarity, some examples around that perhaps, Rob?
I can. So a good example of it, and I believe that you have a graphic that we sent over that shows several wells together. If we could throw that up, that would be. Okay. So an inherent problem with survey tools that included gyros at one point was an east-west direction, where you're actually perpendicular to the force that you're measuring, be it the magnetic field or the Earth's rotation. When you align with the Earth's rotation with a gyro and you get at high angle, you're aligned with the spin axis, so you're measuring the smallest signal. To overcome that, we came out with what we call our GWD 90, which is now our Quest tool that has a solid-state gyros. So we're measuring in 3 different axes, and we're not affected by that anomaly east-west. So what you're looking at here was actually a project that we did, and the company wanted to do some infills wells, but they had problems with their separations. They have, in the drilling world, separation factors tell you how close you are to another well and whether or not you have a chance of hitting it, right? So they wanted to mitigate that and be able to drill these wells farther. So if you look at it, the one on the very bottom that's green, when we got down to the end of the curve and started drilling the lateral, there was a displacement or a difference between the azimuth of about 4 degrees from the gyro to the magnetometer package. Okay. And all they were looking at was the dip angle, and the dip angle came and was just in spec. So typically, they would have just drilled that well, and it would have ended up where that bottom green line is with the bigger circles on it showing the higher limits of uncertainty. But with the gyro, we were actually able to steer it on a straight course, due east, which you can see, and there's actually 2 different colors there. So after we drilled a certain distance, the client was saying, "Are you sure that your gyro is right?" And we're saying, "Yeah, everything's QA/QC'd." So a continuous gyro was run after it to validate it. And then at TD, we ran another one. So the lesson learned from that well was that there wasn't enough non-mag spacing for the magnetometer package. So they added spacing to it, and we drilled the well on the top. And you can see that there's pretty good agreement between the two, which is typically what we would expect between a gyro and a magnetometer package, MWD. And there was about a degree different, which is acceptable. And you can see that the wells ended up where they should have. And even if it was magnetically drilled, it would have been somewhat okay. The third well drilled was the metal one. And you can see again where there's a bust. They ran the same exact non-mag spacing, and there was about 3 degrees different. So that well would have ended up where the red line shows. So what's kind of ironic about all this is that typically people we don't talk to are reservoir engineers. Reservoir engineers get this information to map where the wells are in the actual reservoir, and from that they determine the amount of hydrocarbons they can produce over the life of the well. And many times these wells have been drilled and they're not where they think they are. So that's the really big advantage to having a gyro system, especially east-west, but it can help in any direction.
Okay, so Rob, that's really interesting. So on that graphic, what was the differences between the two surveys in terms of like lateral spacing, where they thought they were and where they actually were, type of thing? You know, was it significant? You know, how many hundreds of feet was it?
Yeah, so one was about 400 feet and the other was about 520 feet.
Okay, so quite significant, really
quite significant.
Yeah. So we actually had a question in from the audience, so I'm just going to try and post it up here. So Joshua Cantu just asked us here, what are some of the best practices of running GWD that you have found that may be different from running MWD? So really picking up on what you guys have just talked about now. What's your advice here to Joshua?
So definitely in east-west, there's anomalies. And I know people can make magnetic corrections. They've done so for a long time. I know there was a study done by Schlumberger several years ago where they took 100 wells in the Gulf of Mexico that had gyro surveys. And they took what they call short caller algorithms or magnetic corrections. And in about 70% of it, these corrections actually brought the magnetic surveys closer to the gyro. And this is something that's been going on for a long time. And they've made a lot of progress with it, but sometimes it's hard to tell based on magnetic anomalies in infield referencing whether or not they're using the right correction to actually place the well. With the gyro, we're, like Adrián said, we're measuring the Earth's rotational velocity, right? It's a stable reference, so we don't have to deal with all the magnetic anomalies that are happening. Magnetometers are actually very accurate. It's just the reference that they're measuring can be affected, causing errors.
Yeah, absolutely. So it's that difference in the physics that or the physical properties that you're measuring. I just wanted to ask actually around what is the size of these instruments? And you know, you're designing instruments for pretty hostile environments in terms of pressure, vibrations, temperature. Can you say a little bit about, you know, what these instruments look like and how well they are designed for these environments?
Yeah, I can speak about that. Yeah, as I said, these are solid state sensors that we are lately using, but we actually have kept the same sizes and pressure. So we put this 3-axis sensor in 1.785 inches pressure barrel. So we have the 3 axes in there with the magnetometers and all the electronics and memory. And we are learning because it's a somewhat new technology, but we haven't had issues breaking these sensors. So we can take the same shock and vibration as a magnetometer. And right now we are using them up to 150 degrees centigrade. And we are evaluating we have a project to go in actually a bit higher on the temperature as well. So it's very comparable on size and shock and environmental capabilities to a magnetometer.
Yeah, and do these instruments run on batteries, or I assume they're running on batteries, right?
Yes, they can run on batteries, and that it's one of the other good features about these new technology compared to the other ones that we are using about 10% of the power that the other ones were. So with a battery, we can have this tool in the ground, well, for several days, 2-3 weeks without any problem.
Okay, so it's sufficient time to drill a well, or at least most
Yes,
wells,
yes,
anyway.
yes,
So,
yes.
okay, so you've talked about the additional accuracy that these gyros whilst drilling provide relative to conventional techniques, particularly MWD, and the differences may be several hundred feet, or if you're metric, several tens of meters, if not more. So that's the sort of the basic value. Maybe this just turn the conversation to talking about some of the wellbore integrity aspects. It's not just a matter of drilling a wellbore along a particular well path. There are all kinds of issues around dog legs and that sort of stuff. So wellbore tortuosity. Let's maybe pick up that subject. So, Rob, talk to us about wellbore tortuosity and why it's important to know about these micro dog legs and the impacts they have on casing, for example.
Okay, so I remember the first time I actually heard the word tortuous or tortuosity was in the 90s, and it was a drilling engineer for BP in Colombia. We had surveyed a well for him, and he asked me, he said, "Well, how tortuous is my well?" And I looked at him and I said, "I'm not sure exactly what you're asking me." But from that, and ultimately what they were looking for was they were running these long vertical wells, and they were having problems with wear on their drill pipe and their casing. So they were running these drill pipe protectors, and they were actually running the gyro to get a better definition of the dog leg, what was happening with it. From that, we've actually run what we call high density data surveys now that we can actually produce 3-dimensional graphs to show how tortuous the wellbore is, and we define tortuosity as the ratio of a straight line to the actual well path over a given distance that we can actually input, which is very informative. It shows a lot of things. We can show where to place submersible pumps in a spot where it's not tortuous, where it won't bend, fail prematurely. Rod guides, we can show the tortuosity in wellbore, points of contact, side loading, things of that nature, which help reduce workover cost, right? Keep the well producing longer, which is a great benefit for the clients.
Yeah. So how have you guys developed this technology? Because it's not, because when we were talking earlier, it's not just the actual survey itself. It's also how you process the data, right, to understand the level of micro dog legs and tortuosity.
Correct. So we've actually been running high density surveys for a long time, and the dog leg from 1 foot data is very noisy, very spiky, and you can read things into it that aren't there. So it's very confusing, and we kind of have been trying to get away from the term dog leg and talk about tortuosity. So doing this, it started out as a study to see how straight wells were that we drilled with a rotary steerable that we had at the time. And so I went to Adrián and his team of software guys and mathematicians, and we were talking about how can we actually view this in a fashion that people can actually understand. So if you look at the graphic on the screen, this is actually something that we did several years ago, and that's 2 7/8 tubing that we surveyed. The client knew that there was a problem with the well that had a leak in it. They pulled the tubing out, and then we surveyed the 7-inch casing, and they pulled the 7-inch casing out down to a point past the leak so that they could replace that. And we drilled or surveyed the 9 5/8 casing. So you can see where that's helically buckled, and that's actually from subsidence. We actually see helical buckling in wells, a lot of unconventional wells, down at the bottom of the vertical portion where they're running long casing strings out into tortuous well bores in the lateral, and they get a lot of friction, and they get kind of rough with it, and it can actually start to spiral at the bottom of the vertical portion, which is where they want to set their submersible pumps. So this information is very useful. for the production people to see exactly what's happening in their wellbore.
Yeah, I mean, this is critical information, as you say. If it's particularly in the unconventionals, if a lot of the tortuosity is beginning to pick up, particularly at that sort of where they start to build out a high angle, then as you say, that's a critical point in the well. Do you see? Go, please. Yeah.
No, yeah. Sorry. No, just to elaborate a bit more on that. I think up to the time that we start looking into the 3D representation and the different parameters, most of the tortuosity or the evaluations of the quality of the well was based on the dogleg severity. So there you're just taking 2 points at whatever given distance you want to see, but you're just looking at the angle difference between the 2 points. And what we found out that, well, the 2 points don't give you enough granularity to see what's going on. So if you have the 2 points every 100 feet or 1 foot, but you cannot see the whole picture. So what we started using was, well, the 1 foot data and looking at the length of a wellbore that makes sense that you can actually see a picture and not lose what's going on in between. So that has been, well, for people to see a representation of the well like this is much clearer than to say, well, you have a dog leg here of 3.7 and here is 2.8. It's not so easy to see, but here you can, well, see the bendings and the nature of it. So
yeah, it certainly makes you think when you see a graphic like this as to just how the helical bending that you have in that inner tubing. It's certainly a cause for concern. It actually brings up a question that I have. Do you guys see a difference given your experience, do you have enough data to show that there's significant differences between the types of directional drilling techniques that are used in terms of wellbore quality, tortuosity, that sort of thing?
I think so. I know that we've done a few studies where companies have gone and they're trying to drill as fast as they can. But this one client that we had, they wanted to evaluate different BHAs to find out which one could drill the fastest wellbore with the least amount of tortuosity. And I think that we've shown that a lot of interaction that's happened since we started this microguide in the end of 2014 is we've gotten involved with a lot of production engineers that have gone to the drilling engineers and said, look at the wells you're giving me. And then sometimes the wells, they didn't drill a crooked well. Like I said, but the effect of running the casing and different environmental issues, they end up with a tortuous wellbore pertaining to the casing path. So there's different scenarios, but definitely we've shown and opened a lot of eyes and upset some drilling engineers along the way.
And something you have to keep in mind is that, well, you see the tortuosity of what you are measuring. So if you look at the data from the open hole, well, you just get an idea of the open hole, and depending on the density, you may have a 100 feet survey or a higher frequency, but that would be the open hole. Then if you run casing and you need to place an ESP on that casing, then it doesn't matter too much how was the open hole. We have seen that sometimes the practices of running casing end up with a crooked casing, and then, well, you really need to measure that. Or if you're looking into production tubing and the wear of the tubing because you have a sucker rod pump, well, you need to survey that and look at that. It doesn't matter too much. The open hole is already history, and you have all these different sections that may, depending on how much tension and compression and how you run that, they may have different shapes, and one doesn't necessarily mean that the other one will follow.
Yeah, I'm wondering what the audience thinks about this. So please, audience, share your thoughts and comments around this. Having seen this kind of graphic showing the tortuosity of different casing strings on what was supposed to be a level well path, audience, please tell us what you think. What does this mean to you? And also share your experience. There's been some questions about, I'm thinking here frac operations, particularly in unconventionals, because if you have too much of a tortuous well path, you may not be able to re-enter and actually complete the well as you intended, you might not be able to reach some of the frac zones that you want to complete. So that is something we'll pick up in another conversation on SPE Live later on. But Adrián, I'm thinking there's been some questions from the audience about costs and that sort of thing for these kind of surveys. So what are some of the barriers for adopting this technology? Obviously, it has value. So what do you see as some of the barriers?
So some of the big barriers we're seeing is the silos in the companies and the budget and who has the money. So whoever drills the well, at least in many cases, their job is to drill the well and they move on to the next one. Whether there was any issue with running casing or setting up production equipment is somebody else's problem. But when we were able to have a more broader conversation with different departments and they look at, well, if we drill a well and then we put an ESP and that will break, and that's $250,000, then 10K for running a gyro. I mean, you can survey a lot of wells, and there have been cases in which they put one pump, it lasted 2 weeks, and then put the second one, maybe because there was some issue, and they break the second one. And so before they call us, they are already running the third pump. So in those type of things, well, when you look at the overall numbers, it makes a lot of sense to try to identify these, measure, because you have to measure before you can do anything, and then you can address the problem or either put the pump in a different place or choose another way of artificial lift. But if you keep all the budget separate and you have the drilling department just drilling wells and then the casing or the completion just doing their side, and then they don't see a lot of the values, and if their KPIs are not somewhat longer term, overall value of the well and efficiency of the process, is hard. So I think if you put everything together, the costs make a lot of sense, and you will take care of this earlier rather than fixing problems. But that's the...
Yeah, thank you. Adrián, you're getting some support here from Andreas Solana, saying that, most of the drilling, or actually it's Rob as well, so, most of the drilling campaigns are very aggressive, so forgetting the production engineer. So, we talked a little bit about unconventionals. There must be a significant difference in uptake of technology between unconventionals, the sort of factory mode drilling, versus offshore wells where the size of the target is very different, and maybe the care and asset value is differently valued. What's your experience between those differences, offshore versus onshore?
So I think the main difference is that obviously offshore, your wells are very expensive. I think a lot more time goes into it. On a platform, you might have so many slots available. If you lose one of those slots, that equates to millions of dollars lost. So it's very important in an offshore environment that they take a little bit better care. And obviously, we know that if you have some kind of an issue offshore, it can be catastrophic, right? So historically, that and formations tend to be a little bit more forgiving and easier to drill in. So, but tortuosity is still a problem. We have clients offshore, they're drilling long extended reach wells. They need to make sure that they get the top part straight as they can. Otherwise, they're going to set their first casing string. They're going to run this drill pipe and rotate it for hours and hours or days, and they're going to wear the casing out, right? As well as their drill pipe. So they're looking into mitigating that, and they take a little bit more time. Land, typically, they just want to drill them, knock the AFE. I remember listening to the director of technology at ConocoPhillips speaking one time, and he said, 5 years ago, it would take three weeks to drill a well that today we can drill in 4 days, 4 or 5 days. So the technology is definitely advanced, but in that advancement, they've lost a little bit of integrity in the wellbore, I think, in a lot of cases, and that's what we've shown In fact, a lot of times the organizations have gotten the different disciplines together, and they're starting to plan things a little bit differently and say, hey, what can we do to mitigate the problems in the vertical portion of the well to cut down on our workover cost, our production cost over the years, and get more value, more return on the dollar.
Yeah, as you say, it's that difference between sort of factory mode thinking, as we have a lot of that in unconventionals, and the more traditional integrated approach that we have in conventional offshore fields. So yeah, very interesting point there. And Adrián, you talked about, location of ESPs, and particularly in unconventional wells. Maybe that's a different way of viewing the asset value and the need, to pick up Rob's point, the need to actually bring in production people for even conventional wells to say, hey, there's a total asset value here, and you need to know the condition of your well to make good decisions. Yeah,
and that's another aspect that I think we have seen, especially in the previous years in the unconventionals, that there were a few companies that will drill wells just to sell the asset later on. So again, in this case, the concern that they have is more financial and short term, and the actual value of the production numbers is not their main goal. So it's depending on the business plan. So some companies may look at the overall value of the asset, and some will look at the first year of production because of the financial incentive or the stock market, and some other may even try to produce a well and they will try to sell it. But there have been some studies looking at several wells and comparing tortuosity with production, tortuosity with NPT, and even tortuosity with the rate of penetration. So under certain conditions, there is a link there, and even what looks like a faster good well, it may be detrimental, and you'll be losing money.
Yeah. No, very good points, particularly in that, again, that asset value and understanding, the well construction and the difficulties and integrating drilling, completion, and production. Something we haven't really talked about, I'm going to kind of put you on the spot here, is plug and abandonment of wells. So, there's a lot of wells out there where we don't have information about the wellbore quality. So, and we need to have some information when we want to go and abandon a well and plug it. So, have you guys had much experience in that sort of field, actually having to go in and survey old wells before they get plugged and abandoned?
We have. There has been a lot of cases, and unfortunately, in a lot of cases as well, you can't access these old wells. Some of them have collapsed at some point, so they have to go down deeper than that. And our gyro well drilling technology has been used a lot. So they have these surveys that are substandard. They don't really know exactly where these wells are. So you have to just go down and look for them. And typically they use magnetic ranging to try to find these wells. But then as they see a pattern where they think the well is, they have to drill towards it. And if they're getting closer to it, they have magnetic interference. That's where our gyro comes into play, where they can actually steal the well and not worry about the interference from the other well.
Yeah. So really the advantage is to have the data to begin with. So
yes,
survey your wells to begin with and have that data. Yeah, that's part
Correct.
of the asset. Yeah.
That's right.
So looking ahead, what are some of the expected changes for you guys looking ahead in terms of activity and uptake of technology?
Well, we are trying to integrate these new technologies into another advantage that I didn't mention is the length is very short. So right now we have the prop is just 19 inches long. So the idea is that we start using this in more tools, integrate this. So we have the information, as you said, on the first place. We are looking into integrating this with some rotary steerables and logging tools as well. So we can, have this data, being able to have a high accuracy survey, at the same time they have the high density of the data to look at the tortuosity and the trajectories. So that's one of the main thing that now that we have this somewhat stable platform that we are working on.
Okay, excellent. So that's that integration and making it the technology more available so that it, yeah, a greater uptake, bringing greater value. Rob, what are your thoughts looking ahead?
Well, I agree. I think the main goal and magnetometer packages, like I said, they're extremely durable. They've done a great job for years. Not necessarily that you need to get rid of them, because obviously, even if, let's just hypothetically say there was a gyro in every one of these systems, it's economical enough at one point. You still have two independent measurements for gross errors, like Adrián mentioned before. That and the fact if you are coming close to an existing well, I found it quite interesting. I know I was actually doing a little bit of work with one of our managers out in Midland, West Texas, and I was looking at surface locations, and I showed him on Google Earth where you can see all these wells, and I said, look at the runway at the Midland Airport. There's like 8 wells right underneath the middle of it. And so as you move around and you see, it's incredible how many wells they have. So a lot of people, what they've done is for years now, they've made it a process to go in and survey some of these with gyros so that they can define where they are, because if they come back and they want to do infill drilling or come from the opposite direction and intertwine them, you need to know where those wells are. And if you don't know exactly where they are, well, if you have a magnetometer package, that helps you detect some kind of interference, so you know something's going on.
Absolutely. Yeah. So again, it's just at your asset value, how you value your well bores and your reservoir and your infill drilling, in particular, after you sort of doing that secondary and tertiary campaigns for production wells. So yeah, very, very interesting, guys. So thank you very much for joining us today and talking about wellbore surveying. It's, I think, a very important subject, something that's probably undervalued in a lot of disciplines, particularly how it impacts the completion and production part of the equation. So thank you for your insights today.
Thank you very much for having us.
Yeah,
Thank you.
really interesting discussion. So thank you very much, and thank you to our audience for all your questions. There was a bunch of really good comments around the surveying and MWD tools, as well as the GWD tools. So thank you very much, audience. Rob, Adrián, thank you for joining us, and have a great day. And we'll talk soon later. Thank you.
Thank you very much.
Thanks. Bye.